Greetings, Algebra 2 students. This is a review for the second quiz over exponential and log functions. So we're going to get into a lot of applications in this review and solving log equations. So initially, if you have a log on both sides and they have the same base, which ours will, then we can drop the logs and then solve the equation that results. And then because we have a quadratic here, we need to move everything to the same side. So we're going to move that 17x by subtracting 17x. And remember, we're moving it to the left side because x squared we want to be positive. And then we're going to move the -3 by adding 3. So whether you write this or you're just thinking it in your head, that 3 is getting added to the 69. And then from there to solve, we need to factor. So we'll be looking for two numbers that multiply to equal the 72, but add up to -17. So it's a positive 72, so they have to have the same sign, but they're adding up to a negative. So we know they're both negative signs in the factors. And then this would be 8 and 9. Doesn't matter which order you write them in. And then you're going to solve each one of those. So remember, those are our factors. Those are not our solutions. So I'm going to add 8. So x is equal to 8. And then to get this x by itself, I would need to add 9. So x is equal to 9. So these are my two potential solutions. And then we should be checking for extraneous solutions. So that has been added to the directions for the quiz as a reminder to check for extraneous solutions. And remember, for logs, anything that would create a 0 or a negative number in the argument would be extraneous. But these are both positive numbers that if I plug them into either of these two places, we still get a positive number. So in this case, both answers are good, so we actually have two solutions. So it can be that you have two and that they both work. All right, problem number 1. Problem number 2. Again, we have logs on both sides, but in this case, we have 2 logs on the left side. And so if we have more than one log on the same side already, we need to condense first. And the bottom of your reference page, those rules for condensing might be helpful to remind you that subtraction, when we condense, goes to division. So this is x plus 5, 12 on the bottom. So now I've condensed. Now I can drop the logs because there's just one on each side. So then this is our equation. X plus 5 over 12 is equal to 3. And we want to solve that equation. So remember, when it is a fraction such as this, where there's more than one part in the fraction, we need to get rid of the fraction first. Or you might have just thought about multiplying these two. Same process, right? On the left, that's going to get rid of the fraction, and on the right, 3 times 12 is 36. Now, of course, we're going to subtract 5, and x is 31. And if I replace the x up here, 31 plus 5, 36, that's a positive number. So The solution is good. It is not extraneous. We keep it. So go ahead and see if you can remember what to do on number 3, how you're going to condense that. Maybe pause me so then you can check your work. Okay, so perhaps you already tried this one. When we condense and it's addition, addition becomes multiplication. So it's still log base 2, but now this is 70x. And if you tried this one, you might have been thrown off because the answer is not pretty, but that's okay. We can have fraction answers, so don't be concerned by that. We're going to still divide by 70. And then do yourself a favor. We don't need to make that into a decimal. This nice 29 over 70 is exact. Done. So maybe easier than expected. And that is a positive number, even though it's a fraction. So it will not create a negative or 0 argument. So it is good. We keep it. So things change on number 4. And they change because now I only see a log on one side. And if we only have a log on one side, we are not allowed to drop the logs. Instead, we need to change the log to exponential form. Get my screen situated there. So we're going to change this to exponential form. So that means that my argument is like my y. Remember, like y equal b to the x. So my argument is my y. Which one is the base? Log base 3. That's how we even read it. Log base 3 of 10n minus 4. Base is the 3, which means this fellow over here is the exponent. And then we're going to have to actually find out what 3 to the 4th is. We can use our calculator. We could just multiply it out, but we should get 81. And then now we just have a nice 2-step equation. So I'm going to add 4, and then I'm going to divide by 10. And in this case, 8.5 is a nice clean decimal. So that decimal is a great choice to use. If you did 85 over 10, you would need to reduce that. So 17 over 2 would also be a simplified answer. So on your reference page, you have that this is equal to log base b of y equals x. So you could use that from the reference page to help you remember how to set that into exponential form. Okay? And then we have a natural log down here on number 5. This is actually an easy natural log problem, but it's really like you either remember or you don't. So keep in mind that natural log is the same thing as if I wrote log base e. So if the base is e and this is e, then this number is the exponent because the base and the log are the same. The base and the argument are the same number. So here, when I see ln of e, because that means this is the base, this whole thing is just whatever that exponent is. So 7 is equal to x. So if you weren't here for the natural log stuff, that may seem a little weird, but I picked a pretty simple natural log thing here. You can just accept that rule that basically the ln and the e take care of each other. Wipe each other out. So ln meaning natural log. from here on out, these are going to be applications, and please read the directions. We might have exponential functions, compound interest, also logs. And you're going to respond to the ones where you're getting a number answer in a complete sentence. You don't need to write a sentence, though, about writing an equation. You're just going to write the equation. But if it says, how much is it worth in 3 years, you can say, it will be worth blank number of dollars and cents. So we should, if it's money, we're going to keep 2 decimal places because we deal in dollars and cents. If it is people, animals, bacteria even, anything like we would consider a living thing, we're going to go whole number rounding, okay? So I think that's consistent with what we've done in class. If it is a number of years, I think in the past we've just said to the nearest 10th of the year, and I believe I've indicated that. All right, so here we're just writing an equation. At this point in A, we have a used car selling for $24,000. So this would be our initial amount. And it depreciates. So the value is going down 20% each year. And remember, 20%, 0.20 when I change it to a decimal. It's going to move 2 places to the left, or you could say divide it by 100. And so that equation, and it's an equation. Now, I don't care if you want to use A for amount, or you want to use V for value, or you want to use Y equal, but it does say equation. So we need something equal. And then our 24,000, our 1 minus, and you could put 0.20 or you could just put 0.20. Same thing as 0.20. We can leave off the 0 in the ones place. It's not going to change the value. And then at this point, we don't know the number of years that have passed. So I'm going to use an X here. Again, for the X, maybe you used T for time. And for the Y, maybe use V for value. So we've seen the formula written with a few different variables, but it needs to be an equation. So that's the first one. That's it. And now you're going to use that equation that you've written to find out the answer for this next question. So how much is it worth in 3 years? So I'm going to take my 24,000, 1 minus 0.20, and now my exponent is the 3. And you could type that in the calculator pretty much the way that looks, or perhaps you go ahead and do this subtraction. And notice if you put it in the calculator and subtract, it's going to truncate, it's going to chop off the 0 at the end. So keep in mind that this or that are the same, okay? So 8/10 or 80/100, same. And then we're going to type that in, and we're going to round it to the nearest cent. All right, I have erased the screen unintentionally and then explained that when I put this in my calculator, because we have all those zeros in the initial number, it's only 3 years, and it's not a complicated decimal. It actually turns out to be a whole dollar amount. And then I've given you a sample sentence. Please place your dollar sign to the left of the number. And then notice this is a sentence. It starts with a capital letter. It ends with a period. It has the subject of the car. You could say is worth. I'm not going to be super picky about your verb tense, but the car is worth, because that's how I wrote the question, I guess. How much is it worth in 3 years? The car is worth. So that would be okay also. All right, on to part C. Still thinking about that same equation that you wrote in part A. Down, down, down. So now it's asking about time, and I've told you here to the nearest 10th of a year, which means we're going to keep 1 decimal place. And we want to know when the value is going to be $10,000. So that's going to be like our ending thing. And in this case now, what we don't know is the time. That's what we're looking for. Time, years. So remember that in a situation like this, first thing we want to do is isolate the base. And remember, this is the base and his exponent, right? So we're going to isolate that by dividing both sides by the 24,000. And then personally, I would kind of simplify that a little bit by like getting rid of some of those extra zeros that they have in common. Because then this is just 10 over 24, which you could also reduce down to 5 over 12, but it's absolutely going to give you the same answer if you leave it 10 over 24. So then I have this. Now, to get that exponent out of the sky, to get my variable out of the exponent, right? Now I'm going to switch to log form. So before I had to switch to exponential form, now I'm going to switch to log form. So log base 0.8 of 10 divided by 24, or 5 divided by 12 if you so prefer. Please do not change that to a decimal because it's going to be a repeating decimal and then it's not going to be exactly accurate. Leave it with the division in there to get the most accuracy. And then that is equal to x. Almost there. Now we need to do change of base because 10 over 24 is not some power of 0.8. So then this is when we do log of the argument. So this is change of base, also mentioned on your reference page. Divide it by, and these are common log now, they don't have a base. Divide it by the common log of the 0.8. And then from here, this is typed in the calculator. So in your calculator, what you're going to type is going to look like this. 10 divided by 24, close the parenthesis, divide it by, press log again, gives you the parenthesis, 0.8, close it, equal, drum roll, and it's not going to be exact, but to the nearest tenth, 3.9. So I could say it will be worth $10,000, just restating part of the question, in 3.9 years. Awesome. So that's that kind of part of the question is the part you would not have done back in Algebra 1B, like using, because we didn't use logs back then. The other part, maybe you remember from before. Okay, that finishes up problem number 6. We'll go to problem number 7. All right, in problem number 7, we're talking about the population of a city. And in this case, growing by this percent, because I haven't said continuous compounding, so then the assumption that we will make is that this is an annual rate. So just one time a year. So very much the same as what we made the assumption before. Annually or per year. Probably could have made that a little clearer for you. My apologies. Note to self. So our starting population, 56,765. It's growing, so we're going to add this decimal. So this percentage is the same as this decimal. So 1 plus 0.046, or perhaps you'll just write 1.046, right? Because it's pretty easy to add that on there. So either way. And then at this point, we don't know the number of years. This is just our generic formula to find the population for any given year. It is population, so we're talking about living people, so we will round to the whole number, yes. And then, so here we're just using our formula, so y equal 56,765 times 1.046, 1 and 46 thousandths. And then exponent, what are we going to use for an exponent? Well, this was the number in 2020, this is in number 2026. So you need to subtract those and think about how many years have passed. Number with an N, number of years since, so 6. So please do not put 2026 as the exponent. You will get a crazy, ridiculously large number that won't be right. So I put that in my calculator and find out that the population will be 74,348 people. I don't recall if that's been rounded down or up, but remember, if the next decimal place was a 4 or less, you just chop it off, drop it. If it's a 5 or more, we've bumped that ones digit up by 1. And then in part C, once again, we'll be using logs because we're looking for time. All right. So we want to know when the population is going to reach 89,000 people. I'm still going back to that first equation I wrote, but now we know that the answer is supposed to be 89,000. It still started out at 56,765. The growth rate is still the 1.046. And the x is in the exponent because we're looking for the number of years. We don't know that. We want to isolate that base and its exponent, so we're going to divide both sides by 56,765. And now that doesn't, you could reduce it some, I know a 5 would go into it, but rather than taking the chance that I'm going to make some mistake in reducing that, I'm just going to leave it with all of that. So I'm just going to go ahead and say 89,000 over 56, or I could write it as division, right? It's the same thing, is equal to 1.0, which is just the same thing I just had without the part that canceled out. And then from there, this is when we're going to change to logs. So we're going to change to log form, what is the base? This guy's the base, right? He's the guy with the exponent. My argument is this ugly fraction. Again, fraction indicates division, so you could write it instead with division. That's how we're going to end up typing it into the calculator. And then we do change of base. And you might pick up on the steps of this and like skip over something that I've written, but I'm trying to just be pretty thorough. And change of base, again, is on your reference page. And so I'm just going to go up here. And change of base says we take the common log of the argument, which is my 89,000. Double check yourself when you're typing all this in that you're typing in the right numbers. The calculator is going to do the work for you, but you've got to give it good information. Divide it by the log of the base, which is 1.046. Once again, when we type it into the calculator, you would not have to like rewrite this on your paper, but just, again, a reminder about how it looks typed in. When you think about the big fraction, you might need like sometimes people forget like some parentheses somewhere. So all that, divide it by, I guess it looks about the same because I'm putting on another line. Close it. Be sure that you're doing the close it, especially that first one. You'll get a very different answer. And in this case, it was like maybe 9.98 or something. So it actually, even if I said nearest tenth, it rounds to a whole number. It will take 10 years. It didn't ask when. If it said when, then we would add the 10 years to 2020 and say in 2030. But it just says how many years. It will take 10 years. So notice how my sentence kind of answers that question for Part C. All right, we're nearing the end, friends. Next up. Now we're talking about compound interest. And that could be for a different number of compounding periods. So in this case, this is quarterly. So quarterly is how many times a year? 4 times a year. If it was weekly, we would say 52 times. If it was monthly, 12 times. If it was daily, 365. Okay, if it was bi-weekly, 26, etc. We can have lots of different options. So here we have quarterly. So it starts out looking very much, so our final amount that is in the account is equal to the generic formula is principal times 1 plus the rate divided by the number of compounding periods, and then the power is the number of compounding periods times the number of years, so that this is the total number of compounding periods. So if it's 4 times a year for 10 years, there's 40 compounding periods. Anytime you're dividing the rate by this, you should also be multiplying the number of years by that same number. It's a little trade-off there. So it means each time they don't give you as much interest each time, but you get it more times, and it gets compounded more frequently. The more frequent compounding is going to result in more money, more interest. All right, so now that is just the formula that's posted in the classroom. That is not your model here. So you could still use Y if you want. I'm just going to stick with A here. So $5,000, 1 plus 0.03, divide it by 4. And then at this point, we know this is 4, and I don't know how many years yet. Or you could put 4x up there. Doesn't have to be t. I'm going to clean that up just a little bit. You wouldn't have to at this point, but if and only if you divide it and it's a nice clean decimal, meaning it does not fill up the calculator screen, then you could just make that a decimal. And so in this case, that does become 1.0075. So the 0.03, divide it by 4. Okay, so it's not quite a whole percent each time. You might want to do that. You don't have to do that, but again. So then here, 5,000, 1.0075, and then this is 4 times 10. So that came from 4 times 10. So my power is going to be 40. And we want the whole value, and that's what we get. We get the final amount in the account. The value will be $6,741.74. Part C of this question is not a log question. It's actually an easier question. Part C says how much interest will be earned. So I want you to think about this. If this is going to be the value of the account in 10 years, and you invested $5,000, what is left if you would subtract your investment is the amount of interest that you earned. Whoa, 74 cents. Or you could say the interest is, or you could say this much will be earned. So part C in that case is simply a subtraction. Because you're not earning $6,741.74 in interest. That's how much the entire investment will be worth at the end of the 10 years. All right, almost there. On the first copies that I made of the review, I had not included this formula. It will be included on the quiz. All right, so this is talking about continuous compounding. So continuous compounding, it also goes along with natural logs, because how do I know it goes along with natural logs? Because I see the E. All right, so when I see the E, I know it goes along with natural logs. And this first part just asks, how much will it be worth in 5 years? Now, I did not make a separate question where you write the formula, because in general, I've given you the format for the formula. So this is what we're looking for. The new amount, our principal is this 20,000. Yep, 4 zeros. and then that's going to get multiplied times e, and then the interest rate, 0.059, times the time are both in the exponent. Both in the exponent. On the calculator, to get E, remember E is second and ln. All right, so second and the natural log button. When that comes up, when you press this, it gives you E to the, and then it gives you a parenthesis. So it knows you need an exponent. And then you could do the math first, but I just went ahead and put all of this in the exponent, times 5, closed it, okay? You could put all of that in and then times 20,000, or you could put 20,000 and then get the E and then the power. But please be sure that you close this. If you put the 20,000 in second and you don't close it, you're raising E to like a much larger power instead of multiplying. So to check to see if you put it in correctly, you should get that it's worth $26,862.53. And then the last part is asking about how long it will take to double in value. So it's a how long will it take? We're looking for time. So it is going to be something that we need to use logs for. And we have a couple options here. Double in value in this case would mean it's going to be worth 40,000. It's starting out at 20,000. And then we have our E. In the power, we have 0.059. We do not know time. Okay. Now, when I said we have a couple different setups that we could use, because what happens when I divide by 20,000? I just get 2. So it doesn't really matter how much the amount is. If it says double in value, you could just start out with a 2 here, and then you do not use the principal. But if it makes more sense to put it there like I just did, you certainly can. And then just like we had done before, if I have a variable in the exponent, then I'm going to need to use logs to get it down out of the exponent. And in this case, because we're looking at E, we see E, then I know I need to use natural log to get rid of that. And natural log over here. And then E 0.059t.